This lecture deals with estimation and is divided into two parts. Part 1 looks at the difference between a point and an interval estimate, confidence intervals, and the alpha risk. And Part 2 looks at the t-distribution and confidence intervals for proportions. So what is estimation? Why is it important? Well, recall that the goal of most research is to collect information about some population of interest. But we often only have sample data on which to rely on. However, we can use that sample data to estimate the value of the population parameter. Estimation is a process by which we select a random sample and use the sample statistic to estimate the value of the true population parameter. And so there's basically two types of approaches to estimation. One is called point estimation, and the other is called interval estimation. Point estimation involves using a single number to estimate the exact value of the population parameter. So typically we use a sample statistic as a point estimate of the true population parameter. So for example, if we wanted to figure out the average income of all Americans, what we could do is we could take a sample and we could calculate their income, and we could use that to estimate the income of the entire population. The problem with that approach is that estimates vary from sample to sample. So if we took a different sample and we calculated the sample income, we'd get a different answer. And so there's an inherent problem with using sample statistics to estimate population parameters. That is, they contain some kind of a random sampling error. And so the sample statistic isn't going to give us the same data or estimate as the population parameter. So we have to use a different approach to estimate the value of the population parameter. And that approach is to use interval estimation, or what you might know as a margin of error. This uses a range of values within which the population parameter can fall. And that range of values is something called a confidence interval. And it's called a confidence interval because it reflects some uncertainty in creating a range of values that's likely to include the true population parameter. In this lecture, I'm going to use the example of calculating a confidence interval for the mean. We know from the Central Limit Theorem that the sampling distribution of the mean is normally distributed. And it has the following characteristics. It has a mean, mu sub y bar, that's equal to the true population mean. And it also has a standard error, sigma sub y bar, which is equal to the true population standard deviation, sigma sub y, divided by the square root of n. And so remember that we have to account for the sample size when we're calculating the standard error, because if we increase the sample size, the amount of variation actually decreases. And so that's why the standard error has the sample size in its calculation. Now, although we know the characteristics of a sampling distribution, what we don't know is where our sample mean falls on the sampling distribution. Now, most likely it's in the middle, because most sample means are actually very close to the true population mean. But it could be anywhere on the distribution. It could be in either one of the tails, or it could be anywhere in between those two tails. So this figure illustrates the shape of the sampling distribution of the mean. Notice that it follows a normal distribution centered around the value of the true population mean, in this case mu, the population mean. Where does a given sample lie in the sampling distribution? Is it here, or here, or here, or here? The problem is we don't know. We don't know a priori where our sample mean is on the sampling distribution. But if we take into account the shape of the distribution and the amount of sampling error, we can determine with some level of likelihood the interval that includes the true population parameter. Unfortunately, we can never be 100% certain that our range of values contains the true population mean, because the normal curve ranges from negative infinity to infinity, and we could have a sample mean that's very far in either one of the tails. So even if we create a range of values that we think includes the true population mean, it may not. Okay, but we can use what we know about the normal curve. We know that every normal curve has a constant area from the center when that area is figured in terms of standard deviation distances away from the mean. So the first thing that we need to do, if we're going to create a range of values that it's likely to include the true population parameter, is to pick some level of confidence. This level of confidence stands for the likelihood that the interval that we create includes the true population parameter. So for example, we might pick something like 95%. Which means that we're 95% sure that the interval includes the true population mean. And so this figure basically shows the areas under the curve corresponding to different distances away from the center. And so you can see that about 68% of the area is within one standard deviation below and above the mean. About 95% of the area is within 2 standard deviations, and about 99% of the area is within 3 standard deviations. And so if we wanted to calculate a 95% confidence interval, we would have to find the area under the curve that includes 95% of the area. And so you can see that if we take the the middle of the curve, and we draw an interval extending, in this case, to about 2 standard deviations, we're going to compute the interval including 95% of the area. And more specifically, that interval has the length that's equal to the product of the z-score multiplied by the value of the standard error, which tells us how much variation we have from sample to sample. And so recall that the standard normal table only gives us half of the area under the normal curve. That is, those areas corresponding to positive z-scores. So in order to figure out the z-score corresponding to a 95% area, we have to take our confidence level, 0.95 or 95%, and divide it by 2. And when we do that, we get a value of 0.475. Now we have to find the z-score in the standard normal table corresponding to that area. And so we first have to figure out which of these two columns to use, column B or column C. And since we're looking for an area between the mean and the z-score, the interior area, we're going to use column B. And so we can see that the first value in this column to include 0.475 is the one corresponding to a z-score of 1.96. And so 1.96 is the z-score that we use for a 95% confidence interval. Okay, now we can use the sample mean as a point estimate for our population mean, and we can use the z-score in conjunction with the standard error to create an interval centered around the value of the sample mean that with 95% certainty is likely to include the true population mean. And so we basically take the product of that z-score and the standard error, which we get from data, and we add and subtract that value to the value of the sample mean, hence creating a range of values that's likely to include the true population parameter. Now, no matter where the sample is located on the sampling distribution, we can be sure with the 95% certainty that our confidence interval will include the true population mean. However, there's also a 5% chance that the interval excludes the population mean, in which case we're going to create some kind of interval that is actually wrong. And so the risk of excluding the population parameter is called alpha, which here I'm designating with the Greek letter alpha. And so that risk is split into both tails of the sampling distribution, because we don't know a priori whether our sample mean is located in the left tail of the distribution or the right tail of the distribution or somewhere in between. And so to illustrate that concept, this diagram basically shows how the alpha risk is split. And so notice that our alpha risk is split in half. Half of it's in the left tail of the distribution, the other half is in the right tail of the distribution. And then in the center of the distribution, we basically have 1 minus alpha, which is basically equal to our confidence level. And so if we pick a 95% confidence level, alpha would be 0.05, and so 1 minus 0.05 is just 95. Here's the general formula for a confidence interval. It tells us to take the sample mean, in this case for the variable y, or y bar, and add and subtract that to the value of the z-score associated with a particular confidence level, let's say 95%, which would be 1.96, multiplied by the standard error, sigma sub y bar. And you can see that the standard error is equal to the true population standard deviation, sigma sub y, divided by the square root of the sample size, n. Okay, so how do we determine the confidence level? Well, we typically rely on conventions. So by convention, we very often use something like a 95% confidence interval or a 99% confidence interval. So what's the difference between a 95% confidence interval and a 99% confidence interval? Well, for a 99% confidence interval, we have to find a new z-score. And so we can determine that by taking the value, 0.99, dividing it by 2, and finding the z-score corresponding to the resulting value in column B of the table. It would turn out to be 2.58. And so you can see that the z-score for a 99% confidence interval, 2.58, is bigger than the z-score for a 95% confidence interval, 1.96. That makes the confidence interval wider, which makes it more likely that we'll capture the value of the true population parameter. So here are the steps involved in determining the confidence interval, and here we're going to illustrate it for the mean. First, we calculate the sample mean, and then we calculate the standard error, again, for using data. We have to decide on our level of confidence and find the z-score from the table. And then we calculate our confidence interval and we interpret our results. Okay, so for example, let's look at the mean education. And let's suppose that we wanted to create a 95% confidence interval for the mean of education. So suppose that we use some general social survey data and we had a sample of 1,972 cases. Suppose for that sample that we found out that they had an average education of 13.53 years. And suppose, for whatever reason, we knew the true population standard deviation, and we knew that it was equal to 3.13 years. Now, that's unrealistic. Most of the time, we don't know the true population parameters. These are the very things that we're trying to estimate. So later in this lecture, I'll show you what happens when we don't have that value. Basically, we have to estimate it somehow. But that introduces more problems. But more on that later. Okay, so what we're trying to do is we're trying to create a 95% confidence interval that's likely to include the average education in the population. That is the population from which the GSS was drawn. Anybody who's an adult, who's English speaking, and who's non-institutionalized. So the first thing we have to do is we have to get the standard error. And so the value that we need to calculate the standard error was given in the previous slide. We need the true population standard deviation in the numerator, 3.13, and we need the square root of the sample size in the denominator, that is 1.972. And so when we divide our population standard deviation by the square root of the sample size, we get a value of 0.07. And so that's our standard error. So now we can plug the numbers into our formula. So the formula for a 95% confidence interval tells us to take our sample mean, in this case 13.52, and add and subtract the product of the z-score, 1.96, times our standard error, 0.07. So when we multiply the standard error by the z-score, we get a value of 0.14. And when we add and subtract that to the value of the sample mean, 13.52, we get a range from 13.38 to 13.66. How do we interpret that range? Well, we can say that we're 95% confident that the actual mean education, that is the true population mean education, is not less than 13.38, not more than 13.66 years. And so if we're to illustrate that graphically, we can see that what we've done is we've created an interval centered around the sample mean that extends to the left and to the right of that sample mean by a value that's equal to the product of the z-score, 1.96, and the standard error, 0.07. Now, if we drew a large number of samples, we would find that 95% of the time the confidence interval would include the true population mean. However, 5% of the time it would not. And the next slide illustrates this idea. And so this figure basically shows us 25 different hypothetical samples, each with a 95% confidence interval centered around the sample mean. And these are all based on samples of size 100. And so notice that the sample means here are illustrated by little diamonds. And they center the 95% confidence intervals. Notice that the sample means are spread throughout the distribution. And that's just reinforcing the idea that we don't know a priori where our sample mean lies on the sampling distribution. And from sample to sample, we're going to get different estimates because of sampling error. So what pattern do we notice here? Well, notice that in the middle of this diagram, we have a vertical line extending beyond the value of the true population mean, mu. And so that marks the location of the true population parameter. And so we can see that most of these 95% confidence intervals actually include that value. However, we have one sample here that doesn't include it. And that's because, again, when we create a 95% confidence interval, 5% of the time we're going to create a value that doesn't actually include the true population mean. So again, this methodology isn't foolproof. There's always some chance of making an interval that doesn't include the true population parameter. So how do we reduce the risk of alpha? How do we create a confidence interval that's less likely to exclude the true population parameter? Well, one thing we could do is we can increase the confidence level. But there's a trade-off for that. By increasing the confidence level, we also increase the width of the confidence interval. And that reduces the precision of the estimate. That is, it's harder to figure out what's the actual value of the true population parameter because the range is larger. And so let's take a look at the values for the 99% confidence interval. And so here we would take our sample mean, 13.52, add and subtract the product of the z-score, in this case 2.58, times our standard error, 0.07. And so this time, instead of getting a value of 0.14, we get a value of 0.18. And when we add and subtract that to the value of the sample mean, 13.52, we now get a range between 13.34 and 13.70. And so to interpret that, we would say that we're 95% certain that the true mean education is somewhere between 13.34 and 13.70. And so to illustrate that graphically, here is a comparison of the 95 and the 99% confidence intervals. And so we can see that the confidence interval for the 99% confidence level is a little bit shorter, but more precise. Whereas the 99% confidence interval is wider, but less precise. So we're more sure that we're going to capture the value of the true population parameter in the 99% confidence interval, but because it's a wider interval, we're less likely to figure out the actual value of the true population mean.